Paul and Tony play a game of chance where two special dice are rolled together. One die has 2 4s but no 3, and the second die has 2 5s but no 6. The outcome for each roll is the sum of the two numbers showing on the dice when rolled. Each game costs 50 cents to play. Here we have a table listing the financial outcome for each event. We want to start by making out a sample space to show all the possible outcomes for the throw of these two dice. So the numbers in each pair of brackets represents the throw of each die. So the first number represents the first die. So the first die is the die that has 2 4s but no 3. Let's suppose that the second die shows a 1. So here are some outcomes for the throw of the two dice. The second row represents all the outcomes for when the throw on the second die is a 2. So I've listed all the possible outcomes for that occurrence, and we can keep going like this. We can generate a third row showing all the outcomes for when the throw of the second die is a 3. So I'll write down just all the throws of the first die, and we can write a 3 in here. Okay, the second die does have a 3. Second die has 2 5s but no 6. So I'll just copy out a few more rows. So this row here covers all the outcomes for when the second die shows a 4. And the next row covers the outcomes for when the second die shows a 5. But we need to list this row again because there are 2 5s on the second die. So these numbers here represent all the outcomes on the second die. 1, 2, 3, 4, 5 and 5. And the values in white, 1, 2, 4, 4, 5 and 6, are all the outcomes for the first die. Well, I'm calling it 1, 2, 4, 4, 5, 6, the outcomes for the first die. We could have called those outcomes the outcomes for the second die. It doesn't matter whether we call it the first die or the second die. Now, I've shown the outcomes for what appears on both dice when they are thrown. But the outcome for this question, the outcome that we're interested in here, is the sum of the two numbers showing on the dice when rolled. So I'm going to write next to each pair the sum. So we have 2 here, 3 here, 5, 5, 6 and 7. We can see that as we go down this column, this number will increase by 1. Well, at least as far as this row. And we have another 6 here. Similarly, going down through this, we have 3, 4, 5, 6, 7, and another 7 here. Similarly here, we have 5, 6, 7, 8, 9, and another 9. And so on. Now, I'm assuming here that the dice are fair dice. So if they're fair dice, all of these outcomes are equally likely. So how many outcomes do we have? Well, we've 6 by 6, we've 36 outcomes in total. And all of these outcomes have the same chance of occurring. The probability will be 1 over 36 for getting any one of these values. Of course, a lot of them are repeated, as you can see. But we need to list all the equally likely outcomes. makes the answering of the question much easier, even if we're repeating some of these outcomes, as you can see in the last two rows. Calculate the probability for each of the outcomes. Well, let's start with the probability of getting a 2. Well, you can see here that only one outcome consists of getting a 2. So that's one outcome out of 36. So the probability is 1 over 36. Now let's look at the probability of getting a 3. Well, we just count the occurrence of the number 3. You can see that it occurs just 2 times. So the probability of getting a 3 is 2 over 36, which can be simplified to 1 over 18. Now let's get the probability of getting a 4. So we count the occurrences of the number 4. Well, we can see that 4 occurs twice. So its probability is 2 over 36, which is 1 over 18. So we put the number of occurrences of the required event over the total number of occurrences, which is 36. Now let's count the occurrences of the number 5. We can see we've 1, 2, 3, 4 of them. So the probability is 4 over 36, which is 1/9. How many 6s do we have? We have 1, 2, 3, 4, 5, 6. 6 6s. So the probability of getting a 6 is 6 over 36, which is 1/6. What about 7? We've 1, 2, 3, 4, 5, 6 7s. So the probability of getting a 7 is 1/6. How many 8s do we have? We've 1, 2, 3, 4. So the probability of getting an 8 is 1/9. If we count the 9s, we have 6 of them. So the probability of getting a 9 is 1/6. We have 3 10s. And we have 2 11s. Now we have 36 equally likely outcomes altogether. So if we add up the numerators of these fractions, we should get 36. So we have 1 and 2 is 3, and 2 is 5, and 4 is 9, and 6 is 15, and 6 is 21, 4 is 25, 6 is 31, and 3 is 34, and 2 is 36. Of course, this should be 36 here. So everything checks out. That means if we add all the probabilities, we will get 36 over 36, which is 1. So the probability of getting any particular outcome has to be a certainty. It has to be 1. We have to get one of the 36 outcomes. How many times should even except doubles come up if this pair of dice is rolled 180 times? First, let's look at the probability of even except doubles. So that's going to be some number over 36. So we need to count the occurrences of outcomes consisting of even except doubles. Well, the even outcomes are 2, 4, 6, 8, and 10. And what about doubles? Well, 1, 1 is a double, so we don't include that. So is 2, 2. 1, 3 gives an even outcome of 4, and it's not a double, so this is included. So is this. 6 is an even number, and the numbers on the die are not doubles. Here's another one. So I've selected all the outcomes that are evens but not doubles. And if we count them, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of getting an even outcome except doubles is 10 over 36. So the pair of dice is rolled 180 times, we want the expected number of even except doubles outcomes for that. So what we do is we see that on average 10 over 36 of all the rolls will be even except doubles. So we get 10 over 36 of 180 rolls. So we expect on average 50 of the 180 rolls to be even except doubles. Calculate the expected profit or loss for this game. So we need to look at the financial outcomes for different events, and I will write these in on the sample space. So we see that if the sum is 7, the outcome is €1. So let's look at sums of 7. For doubles, the win is €1.50. Before I go on, let's write down the probability of getting a 7 or of getting doubles. So to get the probability of throwing a sum of 7, we get the number of outcomes that have that sum, which is 6, and divided by 36. We can of course simplify that to 1/6. What about the probability of getting doubles? We'll count up those. 1, 2, 3, 4, 5, 6. Each of these are equally likely. 6 of them out of 36, which is 1/6. So the probability of getting doubles on the throw of these two die is 1/6. The next event is where the sum is an odd number, except 7. So let's count up those events. We want the sum to be an odd number, but not 7. If we count up these, we'll see that there are 14 of them. So we put the number of these events over 36. And we can see that a win for this event is €0.5. Finally, we have the event that the sum is even except for doubles. So let's highlight those events. These are even numbers, and 4-2 is not a double. And that's it. Sorry, forgot this one. So that actually covers all the outcomes, all 36 outcomes. So what is this probability? How many outcomes are have an even sum except for doubles? 1, 2, 3, 4, 5, 6, 7, 8. Looks like 8. I actually missed one here. You need to be careful here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That makes sense because we have, before we'd covered 26 outcomes, so there are 10 left over. We have 6 outcomes here, 6 over 36, 6 over 36, 6 and 6 is 12 outcomes, and 14 is 26, and 10 is 36. Or you could think of the total probabilities. These must add up to 1, because we've covered all the outcomes. Now let's see what a win is worth here. Well, the win is actually negative here, because if this event occurs, we'll lose 50 cent, but a loss of 50 cent is equivalent to a win of minus 50 cent. So for the purposes of calculations, we can just consider wins, and losses are negative wins. So I will write down win equals minus 0.5 euros. Now we're interested in the expected profit or loss. So we need to calculate the profits for each of these wins. The cost of a single game is 0.5 euros. So we obviously have to take the win, whatever it is, and subtract off the cost of the game, and that gives us the profit. So the profit for this event is going to be 1 minus the cost of the game, 1 minus 0.5. Well, that's 0.5. And so on. The profit for this game here is going to be 1.5 minus 0.5. Well, that's a profit of 1 euro. The profit here for this event is 0.5, the win 0.5 minus 0.5. The profit is 0. Finally, the profit for this game here, or for this event I should say, is the win minus 0.5 minus the cost of the game. Now minus 0.5 minus 0.5 is minus 1 euros. Now I'm going to let the random variable x stand for the profit. And we know it takes on the values that we saw with certain probabilities. It takes on these values 0.5, 1, 0 and minus 1 with probabilities 1/6, 1/6, 14 over 36 and 10 over 36. So we have a random variable that takes on values with certain probabilities, and we're interested in the expected value of this random variable. Now we saw in a previous video that the expected value is got by summing all the values that capital X can take on. They're denoted by small x times the corresponding probabilities denoted by p. So we have to sum these products from I equals 1 up to whatever number we have. Well, n. Well, n, it's n in general, but in this example n is 4. So basically all this means is that we're multiplying each profit by its corresponding probability and summing the results. So we're going to have 1 times 1/6, or sorry, not 1, but profit of 0.5 times its probability, which is 1/6, plus 1 times 1/6, plus 0 times 14 over 36, plus minus 1 times 10 over 36. So this is what we have to calculate. And we get an answer of minus 0.02. Now this answer will be in euros. We're getting the expected value of the random variable x. So x takes on values little x, which are the profits. The profits were, as you saw on the other screen, 0.5, 1, 0 and minus 1. So I'll round this to 2 decimal places. We get minus 0.03 euros. We round to 2 decimal places because in cent this is minus 3 cent. Is the game fair? Well, for a fair game we want the expected value of the profit to be 0. Now in reality most casinos don't operate on this principle as far as I know. The expected value will be some negative number. So the house always wins. But I think the definition of fair here means we want the person playing the game to break even at least. Well, not at least, but to break even in the long run. This particular game is not fair because the expected value of the profit for a game is minus 3 cent. So if a person plays the game, they can expect on average to lose 3 cent in each game. That's what this number means. Of course, they lose or win different amounts in each game, but on average, they will lose 3 cent each time they play the game. So remember, it costs them 50 cent to play the game. So they will lose 3 cents. So after each game, on average, they will have 47 cent. So X is the profit on each game, where the game consists of throwing two of the dice, the two dice in the problem. In the next part, we have to consider making up new rules for the game, which will give a fair game. So basically, we want these numbers to come out to 0. So we could change these values. These are the profits. So that when we do this calculation, we get 0 here. We don't have to bother changing the dice. We can leave the dice as they are. Well, we could change the dice, but that's too complicated. It's probably easier just to adjust these values, just adjust the profits. Well, you could, for example, change this value. We know that 0 times 14 over 36 is 0. This is just 0 as it stands. So we need to work out what number times 14 over 36 will give us plus 3. Because if we get plus 3, then we've increased everything here by 3 cents. And we've brought the expected value up from minus 0.03 to 0. So, we'll just call this x for now. So we have x times 14 over 36. I'll just write it over here. Or 14 over 36 times x. We want this to equal 0.03. So we just divide across. So here is what we get for x. So remember, this value is in euros. All the profits were in euros. So this is, to two decimal places, this is 0.08 euros. Or 8 cents. So if we replace x with 0.08, then the expected value of x will come to minus 0.03 plus 0.03, which is 0. So if we want a profit of 0.08 here, we would have to change this win to 0.5 plus 0.08. So we would have to have a win of 0.58 because the game costs 0.5 and 0.58 minus 0.5 is 0.08. So that's one way we could do it. Of course, there are many different ways we could do it. All we have to do is ensure that the expected value is 0, so we can adjust any of these profits. Or we could change the type of dice that are used in the game so that the probabilities are changed, but that's more complicated. It's easier just to adjust one of these four numbers so that we come out with 0 for the expected value. I just chose this particular number, but it doesn't matter, you can choose any of these four profits.